should manage. More week some activities in the afternoon. Okay, so we have just learned what is Six Sigma. Now we discuss the tools to achieve Six Sigma. So this is the first book on Six Sigma by Michael Harvey and Schroeder. So since it's a smaller class, I think maybe you can keep your can have more interaction. You can keep your mics open, or I don't know whether that allows it. So what is Six Sigma? Can somebody recall? So
Quality improvement methodology, sir.
okay, a disciplined methodology for quality improvement is one of the definitions, simpler definition. Then, so what is the step-by-step approach to achieve this goal? Okay, well, so who spoke now? Harsh Kundra? No. Okay.
Yes, sir.
So what is the process to achieve this goal? How do we achieve this goal?
How to achieve this one, sir? There is a the strategy that you taught us yesterday.
Okay. Okay. So that's what I'm asking. What is that strategy called? Okay. You are again absolutely answered earlier, isn't it? So I'll give the chance to somebody else. Okay. Who is Avinash Chaturvedi? Can you speak?
Yes, sir.
Okay. So what is the process to achieve Six Sigma? What is the improvement strategy?
Sir, eliminates of defects from any process.
No, I mean, what is the plan? How do we achieve that? That is the goal. Okay, what is the goal of Six Sigma? Okay, that is another question. So how do we achieve this goal? What is the goal of Six Sigma?
So eliminates of defects from the any process.
Okay, so that is the goal. And how do we achieve that goal?
So no idea.
If you simply say, I will improve, I will improve, I will improve, will we improve?
Hello.
No, you're not following. Okay, I'll pass on to somebody else. Okay, Munir Ahmad.
Sir,
So can you tell what is the process to achieve Six Sigma? What is the Six Sigma process called? There's an abbreviation also.
sir, some statistical based approach, sir. A breakthrough
That's very
breakthrough
general.
strategy.
What is the breakthrough strategy? So that is the one of the key learning of the first class. Okay, that
Yes, sir.
DMAC approach. What is DMA? I see DMAC. All have forgotten.
So DMAC means, D stands for define, M for measure, analysis, improve, and control.
Analyze, improve,
And control.
Okay, so that is the process. Okay, we'll discuss in more detail today. And what are the tools required to achieve that? So the first step is the 7QC tools. So that is what we'll see today, followed by a case study. So what is Six Sigma? So it is a methodology for disciplined quality improvement. Okay, so the key word is disciplined, how it differentiates from other quality improvement methodologies. So it is very structured, very specific. You have to have a certain organization structure. The goal is clear. Whereas in TQM and all, what is the goal is not clearly defined. You can have, you say you improve as you like. But whereas Six Sigma, the goal is very specific. So that's why we say it's a disciplined quality. And the numerical value is 3.4 defects per million opportunities. So how do we get that? We have just briefly explained in the last class. So this is for a Six Sigma process. So whose standard deviation is 1/12th of the distance between the USL to LSL or LSL to USL, and allowing a 1.5 sigma shift for the centering of the process. So that is how we get this 3.5 defects per million opportunities. We will discuss in detail how to calculate that and all after completing the normal distribution, then we can come to that. So the aim is near elimination of defects, and numerically it is 3.4 dpm. So this was the goal statistically, but people criticize why this 3.4, why not 3.0 or why not 2.8? So there is no real answer. It's an arbitrary goal. So some people say, don't say this. So we have different consultants giving different opinions. Some people say, don't talk about 3.4. We simply say it is, the goal is near elimination of defects, perfection. The goal is perfection. But other people say 3.4 dpm now. Okay. How we get that? We are just seeing briefly. So what is new in Six Sigma compared to other methodologies which were there earlier? So for quality improvement, there have been a lot of methods. Okay. So quality improvement is usually a big business. So each consultant gives his own methods. So Juran had his own philosophy of quality improvement, which is the most famous one, at least in the industry. Deming had his BDA, cycle and all, so which is similar to the DMAC, Plan, Do, Tech Act, or Plan, Do, Study Act, etc. So that is the another improvement methodology. Then Crosby, he had his own step-by-step approach for quality improvement, etc. So what is new in Six Sigma? So one is the team approach. So Six Sigma, we have teams which are cross-functional, not just teams. So in TQM also we have teams like quality circles and all, but the teams are from a particular, usually from a particular, it's not necessarily that it has to be from a department. Unless management forces, people usually will come up with from a single department. And once a team is formed, then it's very difficult to form another team, the same people, or so they try several problems one by one. So that is the difference. Whereas in Six Sigma, management selects the team and it says this is the problem that you have to work on. So team approach. Then customer orientation. Again, this is also controversial. So whether TQM also says you have to focus on the customer. So anyway, Six Sigma people say that theirs is the real focus on the customer. So it's a little subjective. So that's why I say this is all. Six Sigma is perhaps new wine in an old bottle. It's just packaging. So then financial motivation. So this is something which is not adopted by TPM. And many countries this is not done also. Especially Japanese companies, they have achieved Six Sigma quality without saying calling it Six Sigma. Okay, so Toyota and all the many processes, they say the process quality is better. But in Six Sigma, at least in the GE, when they started implementing, they gave a strong financial motivation. So how much money you save from a project, you get 1% of that save. So usually the savings are huge. So 1% of that as a bonus to the team members is a very good motivation. So financial motivation is one of the major differences in Six Sigma. Whereas in quality circles and all, they don't give any financial rewards. So this has been the approach in GE, but in India and all, people don't give financial benefits very much. Even they say so. They say, okay, you are getting salaries for working, then why we should give more money? So it is not adopted by, financial motivation is not adopted by the most Indian companies. I don't know, some companies may be doing, I'm not aware. Then tangible rewards. So promotions and all are linked to Six Sigma, success in Six Sigma projects. So you have to be a black belt to get a promotion. You have to successfully complete this many projects to get a promotion, etc. So such rewards were linked with Six Sigma. So because of that, some people say it had become negative also. So in case there is some problem, even if it's a very simple problem, they will not solve it. And then they will convert it into a Six Sigma project so that they can get the benefits like financial incentives and rewards. Then the use of statistical tools. So heavy use of statistical tools, mass training in statistics and quality. So in TPM, you can do training. Nobody says you don't do training. Nobody says you don't do heavy statistical training, but it is not compulsory. Whereas Six Sigma, it is very structured. You have to have black belt training, at least for 1% of the people. So that means there are, or at least 1% is black belts, 5% of the people, so that all the team members are having the same training. So there is mass training in advanced tools like design of experiments and all, which is very powerful, which can be used to solve problems on the shop floor. Then high impact projects. So this is a major difference. So many times in TPM, the projects are selected by the teams, the quality circles especially, they select their own projects. So what happens, they'll choose projects which are of interest to them. So that may not be of much interest to management. So whereas when management suggests a project, they will choose the projects which are of the greatest consequence, that is financial saving or customer satisfaction, either way. Only such projects will generally be suggested by management. So high impact projects means the improvement will be faster. So even if you improve something, if you don't achieve Six Sigma, even if you achieve Four Sigma, that will have a dramatic effect on the company's figures. So that is the reason for the success of Six Sigma. So high impact projects was certain and tremendous. So the breakthrough strategy, how do we go about improving? So that is what we have been discussing. So the original 8-step approach starts with recognize the problem. So you have a situation, so you have to identify that there is a problem, then only you start improving. So first step is to recognize that you have a problem. If you don't recognize, you never try to improve. Then define it. So specifically, what is that? What is exactly the problem? So define it in terms of numbers and what is the improvement that you have to achieve. Measure the situation. How many defects are there, or what is the loss? Actually measure again. At the definition stage, initially, it may be just a hunch. You may be thinking, or maybe based on some old report. So when you actually measure, you may find that the measurement is not correct. You have to correct it. So then you may have to redefine it, or you have to cancel the project and go for a new project. Anything can happen. Then analyze the causes. what are the causes of the problem? What are the possible causes of the problem? First, and that is the design of experiment control. What are the possible causes that you can verify using design of experiments? And then, once you identify the possible causes, you can try to correct them. That is the improvement stage. So after improvement, you again measure whether you have really achieved the improvement or not. And if not, again analyze. Or if you have improved, then okay, you can go to the next stage, which is control. So you have to develop the systems to ensure that the improvement does not go back, remains there forever. So standardize. So once you achieve the improvement, then you have to standardize it. You change your documentation and all. So in ISO 9000, we have work instructions. All these have to be changed to conform to the current instruction. Then integrate throughout the organization. So if you start it on one machine, then you adopt that on all the machines in the factory, then perhaps other units throughout the organization. Okay. So in a multinational organization, there is a lot of potential for integration. Okay, so this is the breakthrough strategy of Six Sigma. And now we come to the tools for Six Sigma. How do we, or why do we need tools first? So you want to open a lock. Okay, you can break open the lock with a hammer, but it is much easier to unlock with the right key. If you use the right key, it is very easy to unlock. Similarly, improvement becomes very easy if you use the right tool. So what are the tools to be used? That again depends on the quality level. So this is the so-called sigma table and the corresponding defect levels. So as we have said, Six Sigma corresponds to 3.4 defects per million opportunities. So what is an opportunity again? We have to define. We'll see that later. Then 5 sigma corresponds to 230 defects per million. 4 sigma corresponds to 6,200 defects per million. 3 sigma corresponds to 67,000 defects per million. 2 sigma corresponds to 310,000 defects per million. 1 sigma defect corresponds to 700,000 defects per million. So 1 sigma means how much scrap or how much non-conforming. This is per million, so 0.7 non-conforming. That is 70% is non-conforming. 2 sigma means 310, so 30% non-conforming. 3 sigma is 0.067, that is 6.7% non-conforming. So around 7% scrap or rework will be there. So most industries generally are around 3 sigma level. Okay, 2 to 3 sigma level. That means there is a lot of scrap and rework happening on the shop floor. So especially the older companies, many times we see those are not gone for any quality improvement activities. That is the level of defects. So you make so many mistakes, correct it, machining also. So sometimes you have machines only for carrying out rework, etc. So Michael Harry calls it a factory within a factory. So you have a factory inside a factory for carrying out rework and scrap. Scrap, of course, can't be rework. So for rework is a big problem in most industries. Even in electronics, there will be soldering defects and all of this resoldered. Components are good, so only you have to resolder. Somewhere some connection is there. So such rework is there extensively. So that is what is the latent defect. So Bill Smith said there are latent defects. So defects are there in the product which will remain hidden and get revealed when it is used by the customer. Okay, so we have defect level and sigma level. Okay. So 6 sigma is 3.4 defects per million operations. So remember that other things we can easily get from the normal distribution tables. We learned that in the later last section afterwards. Okay, so now we come to 7 QC tools. This is our first set of tools. 7 QC tools are enough to take you from 3 to 4 sigma. So that's what most industries are generally on that 2 sigma level. Means there's no need of any tool. If you simply shout and take proper attention, you'll be able to achieve the improvement. But so just like that, suppose you are a student of reasonable intelligence, then if you just attend classes, you may be able to get 40% marks. But then some more effort is required to get 60% marks to get a first class. And you need much more effort, assuming that the intelligence is average, you need more effort to get a distinction. Same way. So the company which is at low level, if it just attempts implement some systems, they may be able to achieve 3 sigma level. And to reach 4 sigma level, we need at least the 7 QC tools. Then to improve beyond 4 sigma, 4 to 5 sigma, you need design of experiments. So in design of experiments, we optimize the process parameters so that the output is achieved. So this you can achieve 5 sigma. And then to achieve real 6 sigma, you have to design for 6 sigma. That means your product and process all have to be redesigned. So you have to take, so automatically, by just design of experiments, you may not be, sometimes it may be there, but usually you will not be able to achieve 6 sigma. To achieve actual 6 sigma levels, you have to completely design your product and process so that 6 sigma level of quality is achieved. So the first set of tools is the 7 QC tools. So what are these 7 QC tools? They are basically statistical tools, and some are really graphical tools also. Okay, why statistical tools? Why statistics is concerned with 6 sigma? So statistics is the subject of data analysis. So now we have data science has become very famous. But when if you see the contents, it is all almost the same as statistics. So same statistics is coming in several same name or different names. Like 6 sigma is another name for statistical tools. So statistical tools are the key to analysis of data. So 6 sigma focuses on is a data-driven approach. Okay? So you are using data, analyzing the data, and coming up with action plan. Okay, so that's why we need to study statistical methods. And we also have some graphical tools. Why graphical tools? So anyway, this is one explanation. I'm not very sure about how correct is this. So generally our brain, we have 2 halves. So the left brain deals with the logical operations, and usually for right-handed people, the left brain controls the right hand and the right brain controls the left hand. So left brain deals with logical decision making, whereas the right brain deals with intuitive decision making. So your addition, multiplication, etc. is all left brain work. But whereas you recognize a person, you see a person and recognize him. How? So there is something there is a template in your brain. This is a person. He is You don't really think that he's a tall person, he's this thick, etc. Automatically you just recognize. So that is a function of the right brain. Okay, so which is a little difficult to explain how it does. So experiments on people who had damage to the brain. So they show that if one brain is damaged, then such functions are, there are problems in executing such functions. So that's how we come to this conclusion. So graphical tools work the right brain. So that is why we focus on graphical tools. So you see a picture, so that will remain in your mind, and later you may come up with some solution. So that is the power of graphical tools. So that's why we should plot a graph rather than just see numbers. You should always plot a graph. Any experiment, after the results, you should plot a graph and see. Okay, so now we come to the various tools. So 7QC tools is the first that we'll study. Then we'll go for design of experiments. So that will start from the next session. So 7QC tools, they are flow charts, check sheets, histograms, Pareto diagrams, cause and effect diagrams, scatter diagrams, and control charts. So these are the 7 QC tools. Actually, whether some people do not include flow charts in this. Instead, they say stratification as a tool. So this is actually the 7 samurai. So Japanese have in their mythology they have something called the 7 samurai. So there are 7 samurai. That means similarly they wanted to identify 7 tools. That's how the 7 came. And of course we can also say Saptarshi or something like that. So that's how the number 7 comes. So in order to make that, they made it like this. But then stratification is not a tool. That's a principle which has to be adopted in every activity. So that's why later many people have said flowchart is better. So there's no standardization of this. So if you refer some books, you may get flowchart as a tool. If you see another book, you may get stratification. So the original book is by Professor Kaoru Ishikawa of University of Tokyo. He wrote the book Guide to Quality Control. So he meant it as a tool to be used by quality circles. So Japanese, after World War, they started extensive training in quality improvement, and for that, Ishikawa wrote this book on how to use these 7 tools. So there were 7 chapters. So that's how these 7 tools correspond to these 7 chapters of that book. So in that, of course, flowchart is not that tool. It is a stratification. So anyway, we will use flowcharts for since it is more useful. So anyway, there are other advanced 7. So many other tools also have been popularized now. So flowcharts, but the engineers are very familiar with flowchart. So for non-engineers, this appears to be very novel. So when you are teaching quality improvement in the shop floor, so to understand the process, this is very easy. So any process we can view as a series of activities. So switch on radio. Is sound clear? No? Then tune the radio till we get clear sound. I don't know nowadays, of course, this is not there. So FM radios and all, we don't have to tune. We just know the frequency, you just have to punch it in. So I don't know whether this is really valid, whether you are able to follow. The old radio, I don't know if people are using the old radio nowadays. We have to turn a knob and then tune the radio. So if the sound is clear, then we can stop. So usually most of the problems are lying in this feedback loops. So that's why we emphasize this pre-trial loop. So what happens? You may go through this loop several times. Then there is a lot of delay in achieving the final goal. So that is so flowcharts illustrate the steps involved in an operation or process. And then, so many times we can eliminate unnecessary steps and simplify the process. So that itself can lead to some improvement. By just identifying the process. Sometimes some activities will be done in multiple departments. Same activity will be done in several departments. So we can eliminate such activities. So that is all how flowcharts can help in an improvement. Then the second tool is checklists. So this is a simple tool to collect data. So simple forms. So for example, in final inspection, the many times where quality improvement methodologies are not there, there will not be any records. What is happening? Why defects are there? How many defects are there? Nothing will be known. So the first step is to keep a track of the data in the final inspection station. So what are the various defects which are being detected in final inspection? So in a ready-made factory, this is something, broken zipper, number of defects, ripped material, missing buttons, faded color, like that. You keep marking the defects. Then we have histograms. So once we collect some data numerically using step sheets, so if the variable is continuous, you can plot a histogram. So x-axis we have the variable of interest or different categories of interest, but then it is actually not a histogram. It is, if it is continuous on the x-axis, then it is a real histogram. It is corresponding to distributions or probability distributions. So histograms can be used to analyze your process. How is it? So we can compare this process with specifications. We will discuss in detail later this histograms. So a frequency distribution. Each defect, how many are there? So usually we get this simple peak distribution. So that is called a normal distribution. Then, so if you classify the various categories and sequence it in the order of the number of defects, and you can convert into a percentage of the total defects, then we have what is called a Pareto analysis. So actually it should be called Duran's graph, but Duran was a person who was always giving credit to others. So he didn't want to associate, to say that this is his method, so he said this is a principle of Pareto. Right? So Pareto, Wilfredo Pareto, he analyzed the data of wealth among people, and he found that most of the wealth is with just a few people, and most of the people have very few wealth. So that is the Pareto principle. So any organization, we can observe that maybe 80% of the work will be done by 20% of the people. So that is the Pareto principle. So any project team also, 80% of the work will be done by 20% of the people. So usually one or two people will be doing most of the work. Others will be there to take the credit. So that is the Pareto principle. So what problem to attack? So you have identified, so at the final inspection station, you have identified various defects. So which defect should be attacked first? So you can start, okay, highest number of defects obviously should be attacked first. But sometimes you can convert into terms of money. So some defects may be not very costly, it can be easily rectified. Then it is not so serious. But some defects are very costly, results in scrap, large scrap. Then it is more important. So you can convert it to money and then make a table like this, graph like this. And then we can decide on the number of projects to be started. So how many projects should be started? So that again, how much improvement you want, how many people are there, how many project teams can you afford, etc. And maybe 3 or 4 projects we can start simultaneously in the beginning. So to help that, a Pareto analysis, so the biggest 4, top 4 or top 5 may be chosen as quality improvement projects. So to help us choose projects, we use Pareto analysis. Then, once you select a project, now the problem is here. So what are the possible causes of the problem? That we use a cause and effect diagram, also called fishbone diagrams. This is a cause and effect diagram. You can see various, the lines are like a fishbone. So it is called a fishbone diagram, also called Ishikawa diagram, in honor of the person who promoted this concept. The 70s it is necessary. They were first listed out by Ishikawa as the most useful tools for quality improvement. So he is called the father of quality circles in Japan because he was a person who initiated a lot of such activities. He was from University of Tokyo, and he used to give training programs to people in industry. So he was one of those people who were trained by Joran and Deming when they went to, they worked in the US and they went to Japan to help the Japanese industry improve quality. So cause and effect diagrams help identify potential causes of quality problems. So now we are just on paper, we are just discussing what are the possible causes. So these are potential causes of the problem. So finally, then we have to verify whether they are really there or not. Then only we can go for improvement. So how do we verify? So that is using scatter diagram. So you have variable 1, the cause, and we have variable 2, the effect. And then we plot a graph. When variable 1 is increasing, is the effect increasing? Then okay, we have confirmed that there is some relationship between the two. Of course, I always in design aspects will say correlation not equal to causation. But as a first step, we have to start with this. So scatter diagrams are the simplest tool. Okay, of course, to confirm this, really we need to do design of experiments. So to verify relationships between the cause and the effect, we use the scatter diagram. So cause and effect diagram, initially we come up with potential causes which are verified using scatter diagrams. The closer along the line, the better the relationship. So details we'll see later. Then we have control charts. So once, okay, now you improve, you have a cause and effect diagram, you identify potential causes, you attack the most important causes, you verify it using a scatter diagram, then you make the improvement, and then see, measure again how much improvement is there, whether it has really improved. Okay, we find there is a real improvement, then we have to maintain it. So, of course, there will always be variation. So that is the purpose of control charts. So, suppose today you have 8% defects. Today, tomorrow, will you have 8% exactly? No, it can be 9%, it can be 7.5% or 6%. So, there will always be variability. So, to detect whether this variability is within control or is a normal variability or abnormal variability, we need a control chart to track whether the process is stable or unstable. If there are points out of control, then the process is unstable, and you have to first make the process stable. Then only any improvement is possible. So that's why Ishikawa used to say control charts are the start and end of any quality improvement. So when starting, you have to first verify that the process is stable. If the process is not stable, then anything can happen. Today it is good, tomorrow it is bad, day after tomorrow it will automatically be good. We don't know because the process is unstable. So the first step is to verify whether the process is stable. And that is through control charts. Okay, so that we have covered briefly the 7 QC tools. Please study in detail each tool later. Now we'll see a case study how the 7 QC tools were used to achieve improvement. So usually all the 7 QC tools may not be used. So that's why I chose this case study from the book Resin by Asaki Kumar. So this is reducing resin output variation at RICO. So this is the case, QC study. So the background, so this is regarding a quality control circle at RICO's Nimazu plant. So this plant is making PPC toner. So this QC circle has 6 male employees. Their main contribution was that they could achieve a stable quality of resin. During implementation, they held 42 meetings, each 90 minutes long. So this 42 meetings they had. So think of the effort they had taken. And it is not every day, it is usually once a week. So almost a year they worked. And only they were able to achieve this. So first step, so the flow chart. So first we try to describe the process. What is the sequence of the process? So of course we have converted into just first, second, third, etc. So we don't want to divert your attention by giving the technical details of the process. So first processing, so some chemical processing is there, then second processing, then it is divided to half, 2 batches it is divided. Half is processed, same process but into one line and another half in another line. So here it is divided into 2 and each line is processed separately. So third processing, fourth processing is done. Then automatic weighing and packing into large trucks. So this is the process using a flow chart. So technical definition, output is produced amount. So output is how much amount of toner is produced. And yield is ratio of produced amount to theoretical output. So how much you actually produce to the theoretical output. So based on stoichiometric calculations, chemical formula calculations, there is a certain output which is expected. So the yield ideally should be 100. So the yield graph of resin output for reaction tank A. So the yield is sometimes 100, then comes below, etc. So every day yield they are plotting on a graph. And during April 5 to December 21, 1977, it is all above 100. So 43% above theoretical output. So there is a large variation also, sometimes low, sometimes below 100%, sometimes 43% above. So there is so too much of variation. So why is this variation happening? So the first step is to make the process stable. So only when the variation is within control. So you have to have a control chart first and verify that the process is in control. Then only you can really start improvement. So resin output histogram. So this is the histogram of the output in kg. So we can find that there are 2 peaks. 2 peak type histogram was observed. So what is the meaning of 2 peaks? That means there are 2 sub-processes. So of course there was a division into 2 and each process is separated, each part is separately processed. So they divided into 2 batches, separately they plotted, and you get 2 different histograms. Ideally, both should match, but there's a difference of 14 kg in average value. The histograms are not matched. So, understanding the situation. So, you used an X bar R chart, variation between batches up to 48 kg, variation within batches up to 60 kg. So, within a batch itself, there is a lot of variation. So, next step is to identify the potential causes. So, they did a brainstorming session and identified all causes. So, effect is variation in resin output. Why is there so much variation in the quantity of resin output? So, 1, second processing volume extracted, 2, feed ratio, 3, position of reading measurement gauge, 4, automatic weighing, and then each class again we have, okay, there's a major classification, men, that is people, that is men, machine, material, method. So material is the input material to the process, method is how the operation is done, machine is the equipment based problems. So each again you identify potential causes and then we select some causes. So maybe by voting or discussion we decide which cause should be attacked first. But we cannot attack all the causes together. Sometimes we can, so whatever possible we do. So first we attack some of these causes and then okay, sign test, so they will be using more advanced tools also. So sign test is a hypothesis test. Then total volume extracted at the end of second processing. So this is a reduction of within the reduction or deviation within the batch, countermeasure is 1. So they did several countermeasures. I can study of the output for first time and second time. 1/2 extracted for the second processing and studied. Extraction was made for the second processing and then and the output of 120 which is confirmed. Study the output of the feed ratio. So various analysis results are measures here. So they're doing so many things. Okay, we'll not go into the details now. And finally, we verify with the scatter diagram. So there was a 5% significant difference versus for output versus feed ratio. So feed ratio, there is some issue. So the dividing into 2, it's not equal. Okay, so dividing into 12 each, the significant difference between the first and second time disappears. So they did something on that. So there was some mistake in the division. They are doing the chemicals are added, assuming it is equally divided, but actually it was not equal. That was the problem. So again, further countermeasures. Okay. So again, verification using scatter diagram, and then the control chart. So now points are more or less. The variation is much less. Reduction of evolution yield. Variations within batches were reduced. Non-uniformity reduced, but still not completely controlled. So analysis of variation between batches and countermeasures. 3 factors identified. Dividing work after second process. So it is not equally divided. Feed ratio. Automatic weighing process, some mistakes are there. So again, the various activities. Again, we plot using a control chart. Finally, the output histogram after the improvement activities. So things are improved and the spread is very much reduced. So this should be to the same scale as the original histogram. And we can compare that spread, the width is very much. So that is how we can achieve success. So tangible benefits, variation in resin output decreased substantially. Added benefits, reduction in feed ratio, reduction in resin viscosity variation. Intangible results, pitfalls of only average values, importance of daily controls, improvement of daily controls. Measures to prevent backsliding. So now we have to go to, again, define, measure, analyze, improve, now control. Preparation of resin extraction procedure manual, preparation of solvent insertion procedure manual, revision of manual for synthesizing resin, periodic rotation of the automatic weighing process. weighing machine has to be carried. So when different a successful application of this process, we have different terminologies. So simplest is DMAC approach. So this is how the 7 QC tools were applied to achieve improvement.